So this is the expression of the vorticity for the case of velocity in 2D flow in polar coordinates. Okay. Now we will apply for our particular case. In our particular case, they said that VR is 0 and V theta is only function of R. And since it's rigid body rotation, V theta can be written as omega times R. Okay. So if I replace in this relation, first VR is 0, this term will cancel out. So I deduce that for this case, the vorticity is reduced to a z component because it's a 2D flow and is equal to 2 omega z equals to 1 over r del r v theta by del r. Now I will replace v theta by its expression, which is omega times r. So I will get the following. I will get that omega z is 1 over 2 times 1 over r del by del r omega r square. And we know that the derivative of omega r square with respect to r is 2 omega r. So we get 2 omega r over 2r. 2r will simplify. So we end up with omega z equal to omega. Okay. And this is, of course, expected because if you have a rigid body motion, this means that you have an angular velocity for the rigid body that is perpendicular to the plane of motion because you have 2D case. So omega z is equal to omega. Okay. So now we can say that the vorticity in this case is equal to 2 times omega, and which is the angular velocity of the rigid body. Now, we should also define circulation for this body. Okay. To define circulation, we'll go back to the definition. Okay. What was the definition for circulation? We have two approaches where we can define circulation. Or we use integral over a closed surface of V dot df, or we can use integral over A, which is the enclosed area of the curve, of the fixed curve, of 2 omega z df. Now, in this case, because omega z is a constant, okay, we have shown together that omega z equal to omega equal to a constant, then we can move it outside of the integral. Okay, and in this case, we'll have that the circulation is 2 omega integral A dA. Now, it depends now for this integral, it depends on the closed surface we are considering, okay? But what we are sure of is that A is the area enclosed by the contour. So you can take any contour you want. You can directly say that the circulation is 2 omega times the area enclosed by this contour, okay? So we can deduce in this case that for a rigid body motion with fixed angular velocity, the rotation and vorticity are both constants, and the circulation will only depend on the area enclosed by the contour. Okay? Now, in part B, they asked for which particular case I will have an irrotational flow. Okay? So to have an irrotational flow, what was the condition, if you remember? Irrotational means no rotation. If I don't have rotation, this means that omega z should be 0. Okay? And we have demonstrated together that omega z expression is 1 over r del by del r v theta. So this should be equal to 0. Okay? So to have this equal to 0, then this should be a constant. So the condition to have irrotational flow is that r times v theta equal to a constant. And since v theta, in the definition of the problem, is only function of r, okay, then we should have v theta in the form of a constant over r. So v theta, as you can see here, if you have rigid body motion, will be a constant times omega times r, sorry. Okay, and in case it is irrotational flow, it's a constant over R. So in both cases, V is function of R, but in the first case, it gave us a rigid body motion, because in rigid body motion, we have V omega times R. While in case of irrotational flow, to be able to get omega Z0, we should have the condition that R V theta is constant. So V theta should be equal to C over R, to a constant over R. And in this case, for this type of flow, when R tends to infinity, when R, tends to 0, V theta will tend to infinity. So for example, you can have this, you have circular passes like this. And as you are getting closer to your center, your velocity is increasing, okay? So what will happen then, that for this flow, the origin is a singular point where V theta tends to infinity. And if I want to calculate the corresponding circulation, okay, for a certain contour, so if I take a contour enclosing the origin, so if I have, because here the velocity is only function of R, it's not function of theta. So if you take a curve where I have constant distance from an origin, then all points are at a distance r from the origin, then v theta will be the same for all of these points, because v theta is only function of r and not function of theta. Okay, and we have proved that for irrotational flow, this velocity is c over r. So now if I want to calculate the expression of circulation for this irrotational flow, I can consider the following closed curve and say that the circulation is equal to integral over the curve of v dot ds. Okay. Now, what is in this case the expression? So here, to move over the whole curve, theta should vary from 0 to 2 pi. So I should do a complete circle. Okay. And v is the expression of v is c over r, and the expression of ds is r d theta, because here if you consider the circular path, okay, you have that ds is equal to r d theta, and then since the velocity has only a tangent component, so it's along u theta. So when you do if you want ds and v are collinear, this is why when you do v dot ds, you don't have to project, because already the velocity is tangent to the has only a component that is along u theta. Okay, and ds also is along u theta. So in this case, you have v dot ds will give you magnitude of v, which is c over r, times magnitude of ds, which is r d theta. So r will simplify, as you can see, r and r will simplify, and we'll end up with the integral from 0 to 2 pi of a constant times d theta. The constant, you can take it outside of the integral, and the integral from 0 to 2 pi of d theta will give you 2 pi. So we can see here that for the irrotational flow, you have that the value of circulation is equal to 2 pi times the constant c, which is defined by the velocity vector, because v theta is constant over r. Okay, so we have shown that in both cases, the value of circulation is so here the value of circulation for the first case is depending on the area enclosed by the contour, while for irrotational flow, the value of circulation is just depending on the constant of the velocity expression. Okay, so in this case, this is how we can determine the circulation for these two types of. Okay, any question on this? Okay. So we are done for today, and I will post for you also a problem continuation of problems on continuity equation. So as I told you, for the exam you are just responsible for the continuity part, and the first part, okay? And you will have just the problems I provided for you, and I posted the problems on e-learning. So you have for this exam just the first 5 problems, and the part we continued after is will be for the final. Okay. Yeah. See you next time. Bye.